Alright, so I want to move on to a related topic to all the basis theory stuff, but it is a little bit different. At least it's looking at the same ideas but from a slightly different perspective. So I want to move to a topic from linear algebra, and the idea is that we're going to be looking at a matrix. It's going to be a square matrix, n by n, so like 2 by 2, 3 by 3, 4 by 4, etc. And we're looking at this idea of eigenvalues and eigenvectors, and they come in pairs, eigenvalue eigenvector pairs. So we call lambda, that's this Greek letter lambda here, an eigenvalue for the matrix A, and we call V an eigenvector. And here I just want to be very clear that eigenvectors cannot be 0. Alright? So we call V, which is non-zero, an eigenvector for A corresponding to the eigenvalue lambda if it satisfies this equation. AV is equal to lambda V. Alright, so the idea here is, in looking at an equation that looks like this, well, the left-hand side is matrix times, I shouldn't use the cross symbol for multiplication. This is matrix times vector. And on the right-hand side, we have scalar, because lambda is a scalar. We have scalar times vector. Alright, so what eigenvalues and eigenvectors are asking and answering is, to the eigenvalue vector, I'll very often abbreviate eigenvalue to E apostrophe value, or E apostrophe vector. The eigenvalue eigenvector pair is telling you, so it tells us where the matrix A looks like constant multiplication, basically rescaling. Right, because it's saying when is, that's not how you spell multiplication, close enough though, multiplication, I-O-N, because what the left-hand side is saying is multiplication by A, and on the right-hand side is saying is multiplication by lambda, which is just a scalar. Alright, so what this equation is asking is for what values of lambda and for what values of V does multiplication by A look like multiplication by a scalar lambda. Okay, so what you're trying to figure out here is when a matrix is very nice. That's really what you're trying to figure out here. When does the matrix act very simply on a vector? Right, that's the question that we're trying to ask here. So let me give you just a quick example to demonstrate that this is a non-trivial question. Okay, let me phrase it that way. So, all right, let's look at 2 examples. Let me call A. Let's say this is 0, -1, 1, 0. Alright, so this is our matrix A. This is 2 by 2. Alright, so just to remind you of some of the language behind matrices in case you're a little bit rusty. This is 2 by 2, 2 rows, 2 columns. It's square, which, I set up here. We need a square matrix to talk about these things. So this thing is square, and let's look at what it does. Alright, so A, and here I'm just going to multiply it by a vector that looks like xy. Alright, so we can see what this thing does in general. Well, this is going to be 0, -1, 1, 0 times xy. And what is this going to do? Well, we multiply row by column. So go row dotted with that column. Let me put my resultant vector here. Alright, so row times column is going to generate 0x minus y, so that's going to give me minus y. And then the second row times that column, that's going to give us x plus 0y, so that's just going to be x. Alright, so let's draw pictures of what this matrix does. Alright, we can sort of visualize what this matrix does by looking at some specific vectors. Alright, so let's choose simple vectors first. Let's say we start with the vector 1, 0. Alright, so where does 1, 0 get sent? Well, it gets sent to -yx. So, y for 1, 0 is 0, which tells me that the x component of a of this thing, right, we can just write it out. How about that? That'll be easier than me just blathering on about it. A of 1, 0, based on this formula we just figured out here, this is going to be the vector 0, 1. Alright, so A of this vector is going to point straight up. Alright, so this is A of 1, 0. Alright, let's draw another example. Alright, if I start with, let's say I start with the vector here, 1, 1. Right, just choosing simple vectors to work with. Well, use our formula again. A of 1, 1. Right, our formula up here says do -yx, so that's going to be -1, 1. And -1, 1, let me do this in green. That looks like this. Right, so this is A of 1, 1. It's over there. All right, so there's a pattern that I hope you're recognizing here. The general relationship between A of a vector and the original vector. And so what's the relationship? Between A of xy and the original vector xy. All right, what is the relationship between these? Looking at this first example might be the most illustrative one to look at. Hopefully you can see here that they have a right angle between them. And if you look at this second example, it's kind of hard to tell because I drew it slanty, but they also have a right angle between them. And indeed, it's not hard to check that A of xy and xy have a right angle between them always. And this is an easy thing to check because we know how to check for right angles. We know how to dot things. So we can check to see that this this matrix always has always sends whatever vector you plug in, whatever vector you're multiplying by, it sends it to something that's orthogonal to it, to the original. All right, so A of xy has this formula, which I'll use again. All right, so A of xy dotted with xy. And here I'm just going to put brackets around the thing that needs to stay together, right? I can't view this as like A of the vector xy dotted with the vector xy. That makes no sense whatsoever. I need, right, just in terms of things working out correctly algebraically, it's got to be A applied to the vector xy, then dot with the vector xy. All right, order of operations matters here. because matrix multiplication is weird and dot products are a little weird. Okay, so inside the blue brackets here, we already said this is the vector negative yx, and now we're going to dot this with the vector xy, and wouldn't you know it, this is minus yx plus xy, and that is 0. Alright, so the matrix A takes any vector and it sends it to a different vector that is orthogonal to the first, right, to the original vector. So, let's be intrepid little mathematicians here. What does that tell us about the eigenvalues and eigenvectors of this matrix A? All right, so in particular, the question we're trying to answer here is, are there any vectors and any scalars where A looks like it sends a vector to a rescaling of the original vector? All right, so are there any vectors that A is just going to change the length of? That's the question. But keep the direction the same, right? That's really the crucial part about the eigenvalue, eigenvector relationship. You're just rescaling the vector by multiplying by A. You're not changing its direction. And if you look at what A does to any vector, right, just visually, here and here, well, it certainly changes both of their directions. Right? It does not just rescale them. It fundamentally changes their directions. And indeed, if you look down at this relationship here, right, AV is, in fact, perpendicular to V for all V. That's what we just showed in this green circle, the work in the green circle down there. And, I mean, you can't just rescale something and accidentally turn it into being perpendicular unless you rescale it down to being the 0 vector. But that's not what this is doing. So this fact right here, the fact that AV is always orthogonal to V, no matter what V is, this tells us that A can't have any, and here you have to be a little bit careful, it can't have any real eigenvalues or eigenvectors. And I have to throw the word real in there because asking the question about what this does in the imaginary or complex sense is a very different question. I'm not even going to address that right now. All right, so let's just take for granted the fact that we have to confine ourselves to the real scalars right now. It does not have any real eigenvalues because it never takes, right, let's go back up here to the definition. It never takes a vector and simply changes its length without changing its direction. It always changes direction of the vector that you applied to. Okay, so this is a non-trivial question, right? There are matrices that do not just change lengths of vectors. They do more complicated things, even in 2 dimensions, which is the simplest place that you can even hypothetically look at what a matrix does. Even in 2 dimensions, it's possible to have a matrix that behaves badly as far as eigenvalues and eigenvectors are concerned. Okay, so let's look at another example. Let's take A to be something else. Let's not make it as extreme of an example as the last one. The last one is, this matrix here is what you would refer to as a rotation matrix. It takes every vector and it rotates it counterclockwise by 90 degrees. All right, so we're not going to have this matrix do anything as extreme as that. All right, so let's take A to be this matrix 1, 2, 2, 1. Okay. So let's again, we don't have a sense for how to find eigenvalues and eigenvectors, all I want to do is try and impress upon you that that this is a thing that you can sort of reason your way through. You don't need high-powered stuff necessarily to figure out that these things should or should not exist. All right, like in the last example, we only needed the notion of the dot product, and that it tells us when things are orthogonal. That's all we needed to know that that matrix can't possibly have any real eigenvalues. So that's what I mean. We're sort of operating from first principles, so to speak. We're not using any super fancy theorems or anything. So this matrix A, 1, 2, 2, 1. Let's see what A does to vectors. All right, so A multiplied by xy. This is going to be 1, 2, 2, 1 multiplied by xy. And again, you just go row by column. Right, so row by column and dot them together. So that's going to give me 1 times x, so that's just x, plus 2y. And second row by column, that's going to give me 2x plus y. All right, so this thing does something non-trivial to the vectors, right? It's not as simple as the last example, where it was just sort of a mixing of the x's and y's with an extra minus sign thrown in. It's not like that. This is a little bit more complicated. If we draw some examples of what this does to specific vectors, so let me keep my formula there and just draw a picture here, and we'll use some colors here. I'll use maybe red for the original vectors. So let me choose simple vectors again. Let's take my first vector to be 1, 0. And let's use blue for A of 1, 0. So let me just check what that is. A of 1, 0, according to my formula here, is going to be 1 plus 0, 2 plus 0. So that's going to be the vector 1, 2. So that's 1 over and 2 up. So something like this would be A of 1, 0. Okay, so you can see that it does sort of look like a little bit of a rotation, and it also rescales it, right? It's changed the length of the original vector by a bit. All right, for the next one, let's choose something different, maybe -1, -1. Right, I'm just picking random stuff here. And A of -1, -1. This will be -1 minus 2 and -2 minus 1. So that is -3, -3. So if I draw that vector, I get this. Isn't that odd? Right, so if you look at this thing, we have sort of accidentally, and I genuinely mean that was accidental. I did not mean to pick that vector the way I did. We've sort of accidentally stumbled on an eigenvalue and an eigenvector for A. Looking at this, what this tells us is that A takes the vector -1, -1, and it keeps its direction the same, right? This blue vector overlaps the red one entirely. All it did was change its length, and it changed its length by a factor of 3. All right, so what we just discovered here is that A of -1, -1 is equal to 3 times -1, -1. All right, but notice up here, that was not the case. Right? We can't just say that the vector 1, 0 was simply rescaled by a, because that's not true. Its direction was changed, right? Now, if we were to do something like, check 1, 1 instead of negative 1, negative 1, well, a of 1, 1 is 3, 3. It's not hard to check that. Right, so a of 1, 1 is the vector 3, 3, which looks like that. And so if you notice something here, everything that's parallel to this vector negative 1, 1 is still going to be just rescaled by a. All right, so not only is negative 1, negative 1 an eigenvector, but what we just showed here is that 1, 1 is also an eigenvector. And notice that it also gets rescaled by a factor of 3. Right, so a of 1, 1 is equal to 3 times 1, 1. All right, so we have discovered an eigenvalue-eigenvector pair for this matrix, which is 1, 2, 2, 1. Okay? It's possible to find these, and once you find them, again, it's not as trivial as just saying, okay, this matrix multiplies everything by 3. That's clearly not the case, because that's not what it did to this vector 1, 0. Right? I'm coming back to this example here. It took that vector and it did not simply rescale it. It moved it around. Right? It changed its direction. All right, so matrices are complicated things. They don't just act like scalar multiplication, and they don't just act like rotations, like in the last example. They can be multiple things at once. Right? They can do a lot of stuff at the same time. So, hopefully you see that this is a non-trivial question. However, it is a question that is possible to answer, and it is interesting to answer it. Right? It's interesting, if for nothing else, then to at least say that this complicated thing, this matrix is a complicated thing. However, sometimes it is not complicated at all. Sometimes it looks like scalar multiplication. Okay, so hopefully you at least agree with me that that is interesting by itself. Let's move forward to the techniques and the methods for how to actually find these eigenvalues and eigenvectors, instead of just stumbling around, drawing pictures and doing calculations on randomly chosen vectors. Let's instead try to put some method to this madness. All right, so I'm going to give you the super short version of how to find eigenvalues and eigenvectors. The reason why this is super short is because I'm just going to tell you things are true, and you just have to believe me that it works. Typically in a linear algebra course, this is something that I would spend, I don't know, half or maybe 60% of the semester building up to. Here, I'm going to spend 60 seconds building up to it. All right, so the following stuff works. Why it works, you have to reconsult linear algebra. And again, you all had different versions of linear, different professors, different things emphasized and de-emphasized. So for some of you, this may be familiar. For others, this may be completely out of the blue. So I'm just going to tell you these things are true. If you have questions about why, I'm very happy to answer those questions. But I'm just going to tell you what they are. All right, so we have to answer two questions. How do we find eigenvalues is number one. Number two, once we have the eigenvalues, how do we find the eigenvectors? All right, so for the short answer for number one, we solve what's called the characteristic equation. The characteristic equation is the following. You take the determinant of your matrix A minus lambda times the identity, set equal to 0. All right, so this is really the big part of why it would take me most of a semester to build up to this fact. but for right now, I'm just going to tell you this is what you do. All right, you take the determinant of a minus lambda I, and here lambda is your variable in this equation, right? I'm calling it an equation, which means something has to be unknown in it. Lambda is your unknown in this equation. And this thing just ends up being a polynomial in lambda, which you set equal to 0 and then solve. All right? So you're finding the zeros of a polynomial. That's all you're really doing. And I say that like it's not a big deal. That can be incredibly hard. But again, skipping over all the important stuff. You solve this characteristic equation, and then 2, once you have all of the solutions to these characteristic equations, all right, so let's call these solutions lambda 1, lambda 2, and so on, up through lambda k, right? You don't necessarily know how many of these things you're going to get. And here, again, A is an n by n matrix. All right, so a square matrix, so you can actually do this stuff. And the identity matrix, just in case anyone's forgotten. I've used it before in class, but just want to remind you. The identity is 1s on the main diagonal and 0s elsewhere. All right, so it's an n by n matrix, but it is almost entirely zeros. All right, so you get these solutions, lambda 1, lambda 2 through lambda k, and then how do you actually find the eigenvectors is the second question. And what you do is, very simply, you solve a minus lambda I, whichever eigenvalue you're looking at, times the identity, all times v set equal to 0. In other words, right, if you don't like this variation of how I've written this, just remind yourself, using algebra, this is precisely the original eigenvalue eigenvector equation from the first page of this presentation. Okay, so that's all you're really doing. You're just trying to find v that makes the eigenvector eigenvalue equation true. All right, so you're solving this thing for, when I say solve, I mean you're solving it for v, and remember that v is not allowed to be 0. Absolutely crucial that v is not 0. All right, if v were 0, that would tell you absolutely nothing, because the left-hand side would be 0, the right-hand side is set equal to 0, and so you're not actually getting any information out of this. All right, so now let me do a very, very quick example now that we have the two techniques, or rather the 2 steps in the technique written down. All right, so our example was this matrix. So I'm going to look at the determinant of a minus lambda I. That is going to be 1 minus lambda, 2, 2, 1 minus lambda, set equal to 0. This is my so-called characteristic equation. And now I know how to multiply this out. All right, I multiply AD minus BC. That looks like this. Now, there are 2 ways that you could go about this. You could either FOIL out the 1 minus lambda squared and do it that way, or you could add 4 to both sides and take the square root, because this turns out to be a really nice polynomial the way it is. I'll just FOIL it out because that's always going to work. So I get this, plus 1 minus 4 is minus 3 is equal to 0. And this tells me that I get lambda minus 3, lambda plus 1 equals 0. So let's say lambda 1 is negative 1, lambda 2 is equal to 3. And now I'll just find one of these eigenvectors. Right, so a minus 3i v should be equal to 0. And here I mean the 0 vector. And do the work here. I'll write out what you should get. Right, you would have 1 minus 3 is negative 2, 2, 2, negative 2, multiplied by v1, v2 should be equal to 0, 0. It's not hard to check that you get v1 should equal v2. In other words, 1, 1 is an example of an eigenvector for this thing. So I'll let you fill in the details before you move on to the next video.